The second presentation by Marcel Bielefeld approaches it differently. We already have an existing foundation, and instead of putting a new foundation in place, what you can also consider is by reusing that existing foundation, and then of course get an integrated approach. Maybe that existing foundation is not enough. Maybe you need to supplement it, but at least start making full use of that existing foundation in the functionality for the new building. That is the presentation Marcel will give. Marcel, the floor is yours. And maybe Thomas, you can turn off. Yeah, go ahead, Marcel.
Gerald, thank you very much for your introduction. Yes, the theme of this webinar is increased testing saves money, but I'd like to extend that it not only saves money, it also saves time and carbon emissions. Like Thomas told in his presentation just before here, that the construction industry is responsible for considerable emissions of carbon, and reusing can be one of the options in order to reduce this emissions, but also saves money and time. And I'd like to present that today. In a case where an existing building was founded on an existing foundation. It's an old school. I will introduce to you the cases with some pictures of the outside and the inside as it was when it was constructed, show you how it is nowadays, and what the change in the functionality of this school was in order to get a reuse of the existing foundation. It is an old school in the southern part of the Netherlands, and these are the old pictures from the beginning. The school is the beginning of the past century. It's written in Dutch below. It's the room for studying, the classroom. There was a chapel in that as well. An old building with the front facade and the chapel, the staircase, internal staircase. So it's a really old building, including a school, including a chapel and some wings. This is how it looked like in 1923, and this is how it looks like now in 2023. The old school has to be renovated, and for this renovation, the loads on the piles were increased, and the main question was, can we reuse the existing foundation for the new functionality of this old building? The building construction has been finished somewhere in 1917, so over 100 years ago, and has been extended a couple of times in 22, 31, and 55. Thus, the functionality of the building, the new functionality of the building, was the cause for changing in the foundation loads. In general, the loads were increased with about 10%. And it seems to be that the foundation has proven itself over the last 100 years, but there's no archives giving us this information about this foundation. That's how it looks like nowadays, the front with some side wings and the chapel in the back. In the front is the main building. It's constructed in 1917, and later the chapel has been added to it in 1922. A wing and the western side in 1931, and later on an eastern extension in 1955. Some pictures how it looks nowadays and how it looks in the inside, and then we have a look at the foundation. An old school building, apartments in it, and next to that a venue for parties, a restaurant, and some other facilities. In a new situation, the load on the foundations increased of about 10%. And then as a designer, you get a couple of options. The main three are just construct a new foundation, or update the existing foundation, make it suitable for the new loads and the new functionality. And the third, reuse the existing foundation. And the choice you have as a designer is based, of course, about the quality of the existing foundation. We look then at the bearing capacity at the moment, and the durability to guarantee the bearing capacity in the future. And being a civil engineer, geotechnical engineer, or foundation engineer, you want to have a look at the foundation. Well, because the main question you have is, although the piles in a foundation is over 100 years old and has proven itself, still the question remains, is the foundation suitable for the new functionality? And to judge that, you want to have a look into the ground, have a look at the piles. Are you able to, you want to be able to determine the quality of the piles and the capacity of the piles. And we all know that looking into the ground is not possible. That's one of the disadvantages of our profession, but also one of our advantages of our profession. And therefore, some steps have to be taken in testing and analyzing of all the data which is available in these foundations. And we distinguish a couple of steps you can make. The first step you make is an archives study, a study which has been done on your desk in your office, where archives are studied to get some information from the construction and the foundation. And next to that, you have a visual inspection on site. Have a look at the telltales of a building. Are the telltales telling you about failure of certain parts of the foundation? Telltales can be cracks in the facade, or can be unleveled floors. There are a couple of things you can measure or can look at, which tells you the quality of an existing foundation. And of course, important telltale is the settlement. So by monitoring settlement compared to old measurements, or even monitoring continuously for a while, you get some information about the quality of the foundation. And you can test this foundation also on integrity and the quality of the foundation. To guarantee the capacity of the pile, you can make new calculations on old soil investigation, or base your calculations on new performed soil investigation, or just have a check on the old calculation in the archives. And if you want to be 100% sure about the performance of a pile or a couple of piles, just perform load test. If the previous steps are non-conclusive, add a load test to your testing program. So those steps were taken in this cases as well. The main building from 1917 partly was supported by concrete rings of about 1 meter height, 3 feet height. The west wing was founded on timber piles, but there were no drawings of the foundation available. So no information about pile dimensions and pile toe level. The only thing what was known is that the design of the foundation in this main building with the timber piles was based on what is called the Amsterdam method, where 2 piles are situated under a construction wall. This is a picture not from this case, but somewhere else, where you can see where A and B are indicating timber piles with some timber across it, and on top of that, in the length of the wall, some timber, and then the bricks for the construction of the wall. The extension of the building had different foundation types as well. The western extension, which was constructed in 1931, was supported by precast piles, dimensions 300 square, roughly 1 foot in square, and a length of 7 meters. And all those piles had a tapered cast iron pile shoe for making installation of the piles more easy. And the eastern part of the extension from 1955, there's no information at all in the archives. So in this particular case, investment has to be made for either a new foundation or investments in evaluating the existing foundation. Now, investment in a new foundation is the most simplest solution by just making new design, making a new soil investigation, new calculations. And based on that, a rough estimate would have been that a couple of hundred piles should be suitable for only the western part. Piles with a diameter of 0.18, 7-inch, and a length of about 6 meters should be suitable to carry all the load of the new functionality of the building. However, those piles has to be constructed and has to be connected to the existing foundation. So there's a lot of work and a lot of uncertainty in this works as well. So the alternative, which has been chosen for, is to invest in the existing foundation. First, by inspection, evaluating and analyzing is it. Some additional test has been done, and in case that would be needed, to update and upgrade the existing foundation. And in this case, there were some uncertainties which has to be dealt with, especially those for the west wing. There was uncertainty about the pile dimensions, and it was not even clear if the timber piles, that the piles which looked like concrete piles were really concrete piles, or was just timber piles with some concrete caps on it. And instead of inspecting and assuming a couple of things, it was decided to make new CPTs, new soil investigation, and do new calculation on those CPTs, what in case of a timber pile, what in case of a concrete pile. And as that was not conclusive, it was decided to do a couple of static load tests on a couple of piles. The soil investigation exists of CPTs, the Dutch cone penetration test, most likely you're familiar with that as well. And then new calculations were being made, new design calculations were being made. But that was inconclusive, because the capacity varied between, let's say, 200 kilonewtons and 400 kilonewtons, a factor of 2, depending on the pile length. The pile length has to be assumed, as it was not able to measure, and depending with the 0.25 meter more or less penetration depth, the capacity of the pile varied from 200 kilonewton to 400 kilonewton. So that was not quite conclusive. The integrity test, which has been performed on the piles, showed concrete piles, but the varying in the results, depending on the assumed stress velocity, was not sufficient conclusive for the pile length and therefore for the capacity of the piles. As a result, the load test has been chosen, load test to do on the pile as it is. The pile is tested in the current situation with all, including all uncertainties. Uncertainties about the pile dimensions, about the penetration in the bearing layer, what the final blow counts should have been, the integrity of the pile. Just the pile has been tested as it is. The only thing which is uncertain after a load test is the remaining design life of the pile. So the load test has been used here and often in reuse projects to prove the capacity and the serviceability of the existing foundations. And of course, to be 100% sure, you have to test 100% of the piles. That's not necessary, but you have to prove the capacity of a couple of piles and extrapolate those test results on all the piles, also the piles which are not tested. Performing a pile load test can be done roughly in three ways, in 3 methods. You can do a static load test, a rapid load test, or a dynamic load test. In general, if the existing foundation is free for testing, so without a superstructure, all 3 methods are available. But if you test the piles in a preliminary state where the superstructure is still there, or in this case where the superstructure still remains, then the static load test is the most common way to test the piles. In the case of our cases in Breda, the foundation has been excavated, part of the foundation has been excavated, and foundation pile has been disconnected from the foundation beam, and gives us the possibility to put a jackup between load cells, and equipment for monitoring settlements. You see how it was in the field, performing the tests by monitoring the load and monitoring the settlements, and using the superstructure as a counterweight. You get the results for the static load test. That is behavior of the pile. On the horizontal axis, you will see the forces, and on the vertical axis, the displacements indicate the behavior of the piles, its capacity, let's say the ultimate load, and the settlement at working load, the serviceability. The three piles, top and left, were tested, but there was not a geotechnical failure yet, with capacities far over what is expected from these piles. The pile right below is still capacity higher than the working loads or expected loads, but at less stiffer behavior, and even geotechnical failure occurred in that specific piles. However, the capacity of this fourth pile was even giving a factor of safety higher than 1. And this has been proven over 100 years that this pile is capable of carrying its load, or redistributing its force, its load over its neighboring piles. The safety was analyzed as safe enough to reuse all these piles. Well, discussion, which is in general with an analysis of the existing foundation, is that if you don't test all the piles, you have to deal with the test results for all the other piles. The piles were not tested. In this case, the piles has been tested based on a random selection. Quite often you choose the piles which have lower capacity or higher loads, or piles with cracks in the facade nearby. But in this case, there's been a random selection, and then of course you have to extrapolate the results or evaluate the results from your test to all the other piles. And of course, all the piles have worked over the last 100 years. And in this case, it led that there was more load distribution to piles available, which have more capacity, and especially for those piles has stiffer behavior. And all the piles tested have even a capacity which was more than needed. Pile 4 had a capacity higher than needed, and it led to a lower factor of safety, but even the factor of safety was far above 1. So what does it win in reuse of existing foundations? At least in this case, by investments in the existing foundation, especially the evaluating of the existing foundation, the analysis which has been done, the archives research, the evaluating on site, and even the testing, that led to the result that the piles could be reused, and as a result, there was no need for new foundation piles. So in this case, there was the 100 piles which were roughly necessary for this case, responsible for a cost saving of about 17,000 euros, $20,000. But it's more than that, because this is not only piles by bringing to site, installing them and bringing them back, but they have to be connected to the existing foundation, which is a time-consuming activity for a contractor. So those investments were not necessary for the piles. And as increased testing saves money, but also saves time and saves carbon emissions, the reuse avoided 15.5 tons of steel and 30.6 tons of concrete, leading to a reduction of approximately 30 tons of CO2 emissions. And as an indication, this sound not that much, but it's roughly about the electricity of 6 homes in a year. It's relatively small, but it contributes to the reducing of our carbon emissions for the construction industry. So the final quote is that increased testing saves money, and saves money, time, and carbon footprint. That's for me now. Thank you for your attention, and give it back to Gerald.
Thank you very much, Marcel. And you